In this video, we're going to look at a couple of more improper integrals. This integral is improper because it's not defined at one of the endpoints. Now, these are a little bit harder to spot. You know, the ones with infinite bounds are usually pretty easy, but like this one, it's a square root in the denominator, so we need to be worried, of course, about what would make it 0. And 4, well, the function doesn't actually, this does not exist at 4. So the question is, well, can we still find a limit to its area, even though it does not exist at its endpoint? So here I put in a graph, and you can see from 0 to 4 what happens, and we certainly have this asymptote, but the question again remains, can we find the limit to the area? Okay, so we're still going to need to use the correct notation. So I'm going to write this as a limit, in this case as b approaches 4. And because I'm going to do the antiderivative, I'm going to write this as 4 minus x raised to the negative 1/2 power. Now at this point I might think of substitution a little bit. You know, u is 4 minus x, so du is negative dx, something like that. So you could maybe rewrite this, the limit, as b approaches 4, okay, of u to the negative 1/2 du, and we of course now we're going to have a negative out front. Now, to change the bounds, remember we always just plug in the old bounds. Well, this is a little weird because it comes out to be 4 minus b. The bottom bound is 4 minus 0, so it's just 4. Well, now we do the antiderivative. Raise the power, it becomes u to the positive 1/2. Dividing by 1/2 is the same as multiplying by 2. We're still doing the limit as b approaches 4. Now, I might actually resubstitute in, because this is kind of an odd looking bound, and it actually would give us a chance to also just say this is 2 square root of 4 minus x evaluated at b and 0. Makes it look a little bit easier. It wouldn't make a difference. You certainly could have left it, but I usually don't, so maybe this is my chance to actually put it back to what our original problem looked like. So now I substitute b in, so I get 2 square roots of 4 minus b, and I substitute 0 in, so 2 square roots of 4, and I should note that we do have a negative. I dropped it, remember this negative up front, that, so just do this, put the negative out front there. So limit as b approaches 4. Well, now if I plug 4 in, this is the point we do it, for b, I get 0 here. Minus 2 times 2, so 4. Just remember I have this negative out front, so it becomes 4. So what that tells me is that the area from 0 to 4, even though there's an asymptote there, as this function moves from 0 to 4 in that direction, the area approaches 4. All right, in this example, we're going to rewrite limit as b approaches infinity from e to b of, and I'm going to write 1 over the natural log of x times 1 over x dx. That's a pretty easy substitution. U is natural log, du is 1 over x dx. Not too bad at all. It's going to be 1 over u du. We're doing the limit as b approaches infinity. So the bounds, well, plugging these in, of course, the natural log of b is, you know, natural log of b. Natural log of e is 1. So we do the antiderivative. We get the natural log of u evaluated at natural log b and 1. We're doing the limit as b approaches infinity. So the natural log of the natural log of b minus the natural log of 1, just substituting that in. Remember, improper integrals are really similar in so many ways to our old antiderivatives. It's only the notation that's maybe a little tricky. Well, the natural log of, now we substitute infinity in, or we think about the limit. The natural log of infinity is infinity. So this is infinite, infinity minus 0. This is a divergent improper integral. We can't get the answer.